So I'm just going to start recording. So today's seminar is going to be about visual programming, and we have the pleasure to have as a host he's an assistant professor at the Rogers and Research Department, and we're looking forward for your talk. So if you want to start now, so other members will just join later, but we can move forward now. Hello guys, can you hear me?
Yeah, yes. Can I start now?
Yeah, you can go ahead. You can start now.
Sure. Thank you so much.
Thank you for coming.
Yeah. So I apologize for the noises from my background. So someone is working outside, so you may hear some noises. Thank you for the introduction, and I really appreciate the opportunity for being here to discuss our recent research on differentiable programming with differentiable search of program structures with all of you. This joint work with my students Guofeng Cui and Wenjie Chu. So can everyone hear me okay?
Yeah.
Okay, cool. Okay, so deep learning has been used in many applications. For example, so we can use a deep neural network to predict the label of a sequence of input, for instance, a video clip. We can also predict the label for every frame in the video clip as well. And for another example, we can use a deep neural network to navigate a cheetah to jump over multiple hurdles to reach a goal. And we can also use a deep neural network to make a personalized recommendation to the users of a website. So deep learning has achieved remarkable success in all of those application domains. But there's a common concern shared by all of us. It is difficult to interpret the model. The question is why the model make a specific decision based on a specific input. We really don't know because we cannot connect the logic learned by the agent to the uninterpretable architecture of a neural network. So recent years, differentiable programs emerged as a new effective learning representation that intentionally encourages model interpretation. So intuitively, we can learn a program for all the three application domains. So for example, for predicting the label of a video clip, we can use a fold function that fold in the features of every frame in a video clip to an accumulator. And then we pass the accumulator to a softmax to make the final prediction of a label to the video clip. And for the reinforcement learning application example, we can learn a program that behaves like if there's a hurdle in front, and then the cheetah should jump over the hurdle, should make a jump up. Otherwise, the hurdle should just move up, should just move forward to reach the goal. So you can execute this program in a loop to capture the repetitive behavior. And we can also write a program to digest the buy-in history of a user to recommend what she might be interested in buying for the next. Okay. So I will just make a concrete example on why a differentiable program is more interpretable than a deep neural network. So the example is taken from the OpenAI continuous mountain car application. The goal is to drive the mountain car to the top of the valley on the right. Okay, so a deep neural, of course, we can learn a deep neural network for this, but this is again not interpretable. So I show the interpretable differentiable program our algorithm has learned for this mountain car example. So I'll later explain why this program is differentiable. If you just look at it, then it's not differentiable, but we can give a smooth interpretation to the control flow of the program to make it differentiable. intuitively. So if you look at the program, then this decides if the mountain car is to the right of the bottom of the valley, and then we should just drive the car forward. Otherwise, we should just drive the car backward. So this policy suffices to drive the mountain car back and forth in the bottom of the valley to accumulate sufficient energy to eventually come to the top of the valley on the right. Okay, so compared with the deep neural network, so this program is very interpretable, as the program achieves above 90 rewards in the environment, and thus solve the problem successfully. Okay, so the key takeaway from the example is that we want to relate control logic learned by a program with the program structure to make it interpretable. And a programmer is more familiar with programs than the architecture of a neural network in terms of interpreting the logic of the program and then to debug why the program goes wrong. Okay, but there's no free lunch. So in order to get this level of interpretability, we must jointly learn both the program parameters and the program structure. So we cannot use a fixed neural network architecture for a collection of tasks. So we must search the space of program structures to identify one structure that fits a particular task. The challenging here is that the search space of program structures is often discrete and combinatorial. Okay, so if we simply just enumerate every program in the search space and then try to learn the parameters of the program, this is not going to scale to very complicated context-free grammars or complicated tasks. So in this talk, in order to address the challenge, I will propose a differentiable approach to search program structures. Just like how we can use graded descent or ascent to update the parameter of a program, we also want to use the gradient information to optimize the structure of a program until we can identify the best program, the optimal program for a particular task. Okay, and I will use 3 concrete examples from the 3 application domains: reinforcement learning, sequence classification, and the recommendation systems to show how we can synthesize differentiable programs to achieve both interpretability and high performance. So then come to the first example about how we can synthesize differentiable programs for reinforcement learning. If you have any questions about my talk, please just feel free to ask the question in between the talk. Okay, so reinforcement learning is the process of learning an agent to interact with an environment. After executing an action, the agent receives a reward, and the goal is to maximize the long-term accumulative reward. Okay, and the goal here is to learn a policy to achieve the maximum long-term accumulative reward one can get. And the policy is a function or a map from states to actions. Okay, so in terms of the representation of the policy, we can just use any differentiable function with the parameter theta. And in order to update the parameter theta, we can simply just update the parameters by taking steps along the gradient, along the policy gradient estimated by a batch of rollouts by planning the policy in the environment. So this is just a standard reinforcement learning. But in order to apply policy gradients to update a policy, we need the policy representation to be differentiable. But typically, programs are not differentiable. So in the state of the art of programmatic reinforcement learning in terms of learning a program in a domain-specific language as a policy to control a reinforcement learning application, we typically need to first use a deep reinforcement learning approach to learn a deep neural network. And then we try to use imitation learning to distill the deep neural network into a program. So we want the program to approximate the output of the neural network. And we also learn the program using data generated by the program itself to address the distribution mismatch problem. So there is an iterative imitation learning loop in order to get the best program from a given oracle. And this is all because a program is not differentiable. So we have to perform imitation learning like this. But there are two problems or challenges with this approach. First, in order to find a program that approximates a neural network, we need to enumerate a vast number of possible programs in the search space to see which structure of a program can give you the best approximation accuracy. And second, it turns out that after imitation learning, the program we can get has usually has a worse performance than the oracle. So the program cannot get as much rewards as the oracle oftentimes.
Sorry, what is F and L in this slide?
So F is a function, or F is a domain, F is a program. So we want to find a program F to approximate pi theta, where pi theta is a learned neural network. So we want to find one function F that approximates a neural network. So F is a program which is typically not differentiable.
Okay, and then L is the search space?
Like in the argument.
Oh, so L is like the space of functions you can get from a context-free grammar.
I see. Okay. Thanks.
Yeah, we want to find one function F from the possible space of functions to approximate a neural network pi theta. Okay. So there are two problems. One is first, we need to enumerate a lot of functions F from the search space. And the second, the performance after imitation learning is not as good as the neural oracle. Okay. In order to address these two challenges, we first try to kind of compress the search space. So we develop a compositional programmatic reinforcement learning. So we want to compose primitive functions into complex behavior to solve novel RL problems. Okay, so we'll give you a concrete example. On this slide, we have context-free grammar used to define a space of programs from which we can choose. Okay, so we want to find one program from the space defined by the grammar to control a reinforcement learning application. And E here is the starting non-terminal symbol, which represents a high-level program structure. And E can be unrolled as an X here is the program variable, like what is observable to the program. And C here represents a low-level controller. So the low-level controller in this talk is assumed to be some combination of primitive functions. And a primitive function can be like a pre-trained neural network that captures some task-agnostic basic skills. So let's go back to the cheetah example. So in order to jump over multiple hurdles to move to the goal, we can equip this domain-specific context-free grammar two primitive functions. One is the cheetah jumping up. The other is cheetah moving forward. So we can pre-train jump up or move forward as two primitive functions implemented as neural networks. And a low-level controller is a combination of these two controllers. And we also allow if then else in the program. So intuitively, this can be understood as we switch back and forth between the low-level functions. So in certain conditions, we want to invoke one low-level function, and in other conditions, we may switch to a different low-level function. And for the cheetah example, it's like when we find the cheetah is very close to a hurdle, and then we may want to invoke the jump up function. And if the cheetah is, if there's nothing in front of the cheetah, and then we may want to invoke the move forward function. So we switch back and forth between these low-level primitive functions to compose them to a complex program to solve a complex RL problem.
I have a quick question here about the CPy. So I'm wondering here, CPy is the space from which you sample a given C? Or
CPy here is ensemble policy. So we just ensemble pre-trained primitive functions. And theta 1, theta 2, or theta n are parameters going to be learned. So we want to learn how to combine the primitive functions together to get new behavior. So for example, if you have agent.
I understand. But how does CPy fit into E and or B? So in E or B, you don't mention CPy. I'm wondering.
Oh, so here this C can be like CPy.
I see.
So yeah, just want to make an example. So CPy could be a combination of pre-trained primitive functions, or CPy, or C can be other things. So for example, C can also be some PID functions. If we know that PID could be used here to control an application, then we can use the if condition to switch between some PID controllers to control the application. So, and C can be implemented as whatever you want.
Okay, and I'm wondering, have you stumbled across the term stun, or like synthesis through unification? I think this is an example of that. Okay, thank you.
Right. So this is our simple grammar for this, and yeah, I just in this talk I just limit C to be some combinations of some primitive functions pre-trained using neural networks. But as I have said, CPy can be anything as a low-level controller. So we use this as a way to comprise the large search space, so we can then build hierarchical controllers to use prior functions for dealing with new tasks. And the second thing we modified is that we give differentiable program semantics to this context-free grammar. So previously, so in the state-of-the-art programmatic reinforcement learning, we just execute the program as a discrete one. So in that sense, we have to use imitation learning as the program itself is not differentiable. But this has the problem like the learned program that cannot have a performance as good as the oracle. And then we want to just use reward signal to update a policy. But in order to do so, we have to make our program differentiable. So we associate this kind of semantics to this kind of semantics to an if then else. So and the sigma here represent a sigmoid function. And the intuition here is that if the value of B is significantly greater than 0, and then the result from the then branch dominate. If the value of B is very close to 0, and then the result from the else branch dominates the final result. So by giving a smooth definition to the conditional constructs in the program, we make the program differentiable. So we can then directly use reinforcement learning to update our program. So I'll just give and here I represent a low-level observation to the low-level controller. And the theta are going to be learned by reinforcement learning. So I'll give you an example of a program, of a differentiable program learned in our experiments to show, to convince you that why this kind of program is interpretable. So in this application, we have an AND cross maze. We have the musical AND as the bottom of the AND cross maze. And we also have 3 random goals in the environment. And at each iteration, one of the goals would be sampled. So the agent needs to be either just go up to reach the goal, or go up and then turn right to move the goal on the right, or go up and then turn left to get the goal on the left. So this is a very complicated behavior the agent needs to learn. And in fact, if you just apply straightforward reinforcement learning to it, this environment cannot be solved. The program.
I have a quick question. Sorry to so you mentioned that these are pre-trained primitives moving up, down, left, and right. Did you find that if you were to have trained, and so that in the one of the original problem formulations you posed, you were talking about this bi-level optimization where you're learning the parameters at the same time. If you were to have done that in this setting, or did you try that, and did you find that it was intractable to try and learn these control primitives jointly with the structure of the program?
Are you talking about whether we should also learn the parameters of these primitives?
Yeah, or whether it was attempted. I was curious to see if I mean the tractability of it, because I know these are complicated things to learn, and generally people use neural networks for this.
Yeah, we also try to just learn those primitive functions with the policy, but this doesn't work because unless we have a way to regularize the behavior of those 4 functions, so that in learning we also learn pi left is just forcing the agents to move left. But we didn't try that. So we have just tried predefined primitives. So it's still a research question regarding whether we can co-learn both the high-level programs and the low-level controllers.
Thank you.
Yeah, sure. And in this, in our work, we just focus on learning how we can compose low-level controllers in a specific branch, and how we can also learn the theta values to learn the conditions of if. And we also try to learn what is the structure of the program. And learning the primitives together with the program is a very interesting research direction. Okay, so let's just see why this program is interpretable. And the program can observe action Y, which represents the current position of the agent, and then GX/GY represents the goal position. So at each iteration, one of the random goal would be sampled for the agent to reach. And we also equip the DSL with 4 primitives trained in the musical environment for an AND to go up, go down, go left, and go right. So they are already in the DSL. The program we learn is like this. If you just look, so the program consists of 3 branches. If you just look at the program, you find it's not very interpretable. Hello? So, okay. So, but we can show the branch activation graph of each Boolean condition. So recall that we interpret the semantics of if then else using sigmoid. So in order to know where this branch take the dominance, we can just draw the sigmoid value of this condition. So if you look at the map can take the x value from -8 to 14, and the y value of the map can take values from 8 to -8. So we just draw the sigmoid value of each point in the map using the Boolean condition for the if. Okay, so we draw the branch activation for branch 1 in the picture here. So this means this shows that in which region of the cross maze the then branch or branch 1 dominates. And similarly, we also show in where of the map the third branch dominates. The third branch is the branch condition of the third branch is 1 minus the sigmoid value of the first branch of the first Boolean condition times 1 minus the sigmoid value of the second if condition, because you have to negate both the two Boolean conditions in order to reach the else branch. So if you look at the branch activation graph, you would find out that at the very beginning, the first branch dominates. And as when you get closer to the goal, the third branch dominates. So if you look at the first branch, and then the primitive function pi up dominates. And if you look at the third branch, the primitive policy pi right dominates. So this shows that at the beginning, we try to go up, and at a certain point, we try to go right in order to reach the goal. On the right. So we draw the activation graph specific to the goal position where x is 6 and y is -6. And this shows that why the program is interpretable. Based on the Boolean condition, we switch different primitive functions in order to make an up and a right curve in order to reach the goal. And you see that.
So is the program structure something that was fixed throughout training, or is it something that was that the algorithm learned?
The structure is going to be learned.
Okay.
Yeah. So I'll just show why this program is interpretable, and later I will see how we can learn the structure and the parameters as well.
I'm wondering, how did you? So I saw that you used a differentiable rule for backpropagating through the grammar, but I'm wondering, was there any sampling involved of the structure, or was it purely done with backprop?
I'll be there in a minute.
Okay.
Yeah. And if you look at,
I'm curious, like, is the program that you're learning deterministic, or are you treating it stochastically? Like, are you passing, like, for this first condition, first Boolean condition, if theta1c plus theta1 transpose times x greater than 0, is that a hard condition, or are you passing that through a sigmoid and then like sampling that, with probabilities, that sigmoid, you take the first branch, and then with 1 minus that probability, you take the second
So we
branch.
just take the sigmoid value of that. So the output of the program is deterministic. But when we apply reinforcement learning, the output of the program is only the mean value of a normal Gaussian policy. So we can still then use stochastic policy gradients to update the policy. And in reinforcement learning, we also learn the sigma of the policy. So the program only outputs the mean value.
Sorry, what do you mean by the mean value here? Like, what's the distribution?
Yeah, so because we assume a stochastic policy, and the program just outputs the mean value of the normal distribution, and we also need to learn the delta of the policy.
Okay, and how do you learn? Have you?
So how to learn this is delegated to reinforcement learning. So even you have a neural network, the neural network just give you the mean value of the Gaussian policy. And then reinforcement learning would also need to learn the sigma of the policy. So this just, so our program is just like the neural network policy here. It only outputs the mean value.
Okay.
And it's
Thanks.
up to reinforcement learning to figure out the sigma of the Gaussian policy.
All right. Thanks.
Okay. So if you look at the program, then you find that so actually this part of the program is never executed because branch 2. So this part corresponds to where branch 2 would be activated, and branch 2 will only be used when the goal is sampled as 6, 6. Okay.
So another question is like is X a handcrafted like feature vector, or is it the robot state given by the environment? Like,
so X here is specified as what is observable to the program. So X includes the position of the end and also where is the current goal.
Okay, thanks.
So if the goal is fixed to 6 minus 6, and then we have the branch activation. And if you switch to a different goal, the branch activation would be also changed. So for example, if the goal is that to be here, and then you would find that the activation graph for branch 1 is like this. So everything here is in yellow. So we would almost just use type up to go up to get the goal on the top. Okay, so let's see how we can learn both the structure of the policy and also the parameter of the policy. So enumerating each policy structure and train each with reinforcement learning is computationally infeasible. Okay, so even we have a simple grammar like this, if you do an enumeration, and then we need to extend E to C and C to a policy ensemble, like the CPI in the previous slide, or we can just unroll we can expand the non-terminal E to if then else. So we have a choice of either expand E to a policy to a low-level policy C or to a if then else. So we can continue to enumerate more and more complex policy structures and then use reinforcement learning to learn the parameter for each, but this is not going to scale. So we want to jointly learn both the policy structure and the policy parameter. And in order to do so, we represent all policies by its program derivation. So consider the non-terminal symbol E, which is the starting symbol of the grammar. So we have a choice of whether we expand E to just a low-level controller C, or we expand E to if then else. And we can also, for the E2 here, we also have a choice of whether we expand it to low-level controller C or if then else. And so we also do the same thing for E3. So E3 can be expanded to low-level controller C or can be expanded to a if then else. So we have many choices, but we can merge all the program in this program derivation tree. And it turns out that what we really wanted to do is to optimize the probability distribution of all program structures in the program derivation tree. So the program derivation tree records all programs that can be derived from the starting symbol. And we relax the category choice of discrete rules to expand a non-terminal to a softmax over all possible rules to expand the special non-terminal symbol.
So as I understand here, you're basically like unrolling the space up until a certain depth, and then you just do backprop on the entire thing.
Yes.
Wow.
This is not going to scale later, I also need to introduce some optimization to make it scalable. Okay, so we have all the programs in the program derivation tree, and we can also interpret the program derivation tree as a program. The output of the program derivation tree is the normalized weighted out the normalized output of all the programs embedded in the program derivation tree, weighted by the probability. So for example, we may have learned that at the very beginning, we only have a 1% probability of expanding E1 to a low-level controller, and 99% probability to expand E1 to if then else. And we can do this for every category choice. And the goal is to learn the probability distribution of high quality program structures in the space of programs. So we just relax the discrete policy structure search space to be continuous. And in terms of learning, we want to learn both the structure width and the policy parameter by level optimization with the policy gradient. So we still want to maximize the long-term reward that can be achieved by this policy. We alternate learning the structure width W and the policy parameters theta. Okay, so at one iteration, we will fix the program parameter theta and only use policy gradients to update the structure width. And as the next iteration, we will fix the structure width and then learn the policy parameter theta. So by alternating learning structure width and learning program parameters, the algorithm converges to the best policy that can the best policy structure and the best policy parameters to maximize the long-term rewards. And after learning, we can then vote the best program from this program derivation tree regarding which program has the highest probability to eventually maximize the long-term rewards, which one is the best among all the programs embedded in the program derivation tree.
Sorry, I have a question. How do you evaluate the objective value for this derivation tree? You said it's the weighted reward based on the rollout, but you have to choose a sequence of discrete actions, right?
Oh, here we just, so here is a continuous reinforcement learning application. So the output.
Oh, I see. Okay, I see. So that's why it works. Would it work for discrete action spaces, or is this pretty focused on continuous?
We believe it will also work for the discrete action space. So for there, so each branch needs to output the distribution over the actions. And then we also need to take a normalized sum from all the branches and from all the programs.
And you would sample from that distribution. I see.
Yeah. Okay, so this strategy turns out that this simple strategy works for this simple grammar, but you may have already observed that for very complex grammar, then the program derivation tree would itself become very complicated, and we have to introduce some optimization to make it work. But for this reinforcement learning task, this is already sufficient. So we have evaluated this program in some challenging reinforcement learning applications. So for example, for the AND cross maze, we have already talked about this. We want the AND to reach a goal from the 3 random goals at each iteration. And for the AND, and for AND random goal, we want to learn a policy that can reach a random goal, randomly sampled at anywhere that could be at anywhere around the end. And for half cheetah, we want to train a cheetah to jump up over multiple hurdles to reach the final goal. And for the pusher, we want to learn an agent that can push an object to a fixed goal region. So for the ant environment, we associate the domain-specific policy language with primitives such as going up, going down, going left, and going right. And for cheetah, the primitive policies are like jump up when it encounters a hurdle, or it just move up, just move forward. And for the pusher policy, for the pusher environment, the two primitives are push left and push down. So we show the experimental result here. Just like the curves in red is our algorithm. So we compare our algorithm with TRPO and PPO. We also compare our algorithm with compositional SAC. So in compositional SAC, we also give the neural network the 4 primitives. And also we use a neural network to choose which policy, which primitive we should use at a certain step. So the only difference between compositional SAC and our algorithm is that we use a program to choose which primitive to take at a certain point. But in compositional SAC, we use a neural network to choose which primitive to combine. So it shows that both compositional SAC and our algorithm significantly outperform TRPO and the PPO. So TRPO and PPO cannot even learn for other environments. And our approach significantly improves compositional SAC in half cheetah and the pusher. So in terms of the uncross maze and random goal, compositional SAC and our algorithm essentially performs similar, but compositional SAC is way more sample efficient. We believe this is because because SAC is off policy and TRPO is on policy. But our algorithm can be used with any reinforcement learning algorithms. So we also compare the final performance of our policy with compositional SAC. It shows that our policy outperforms compositional SAC in the final performance in terms of how close the agent is to the goal. Okay, so our algorithm is slightly better than compositional SAC, and more importantly, our policy is way more interpretable. And we also measure the sample efficiency of our approach, this column shows that how many samples in millions we need to train a policy, to train the program derivation tree. And after training a program derivation tree, we also need to take additional samples to fine-tune the policy voted from the program derivation tree. So after we select the best structure from the program derivation tree, oftentimes we need to continue to train that structure in order to make it recover the good performance of the derivation tree policy. And we compare this with just training the policy from scratch using the best structure voted from the derivation tree. So this shows that oftentimes the samples needed by training the derivation tree and training the program selected from the derivation tree altogether takes less sample needed than training a policy from scratch. And perhaps this is because the derivation tree is an over approximation of all of the needed policy. And more importantly, it shows that if we enumerate every policy structure in the program derivation tree, this would take a lot of samples. But our algorithm trains the probability distribution, and also where our policy trains the policy structure and the policy parameters together. And in this way, we can save a lot of samples needed, which are otherwise required by policy enumeration.
So what is a sample in this case?
Sample, like how many samples we need to make in the environment in order to estimate policy gradient.
And so what is a sample?
Take a action in the environment and see what is the reward can be received.
I see. Okay. And on how many different? Well, I see you have like 4 tasks here, but for example, in the pusher, right, the red circle can have a different location, right?
Yeah, for that one, the object can be at random location. The target in red is fixed.
I see. And so how many of those random locations do you try to?
Oh, it's just randomly sampled. So in learning, we sample 50 trajectories.
Okay.
At each iteration.
Okay, sounds good.
Okay, and we also compare our approach with oracle-guided programmatic reinforcement learning. This is like we first train a neural oracle, and then we try to synthesize a program to approximate the neural oracle. It shows that our oracle-free approach significantly outperforms oracle-guided programmatic reinforcement learning. And the reason is because it's not necessary the best program in the space approximating the neural oracle is also the best program for the tasks. So this shows that directly using reinforcement learning to optimize the programmatic policies can get us better performing policy. Okay, so I'll skip this. In summary, we just—
There's also a question in the chat. I don't know if you can see the chat.
Oh, yeah.
Or I can read the questions. So the first question is, what's the most scalable programmatic policy that you have? And what problem do you expect when scaling the complexity of the programmatic policy?
What's the most scalable programmatic policy?
Yeah, I guess just roughly the size of the program part.
Okay, so yeah, we evaluate this. We limit the abstract tree representation of a program to be 6, and this is the actual depth of the AST of the learned policy in average, taken from 10 runs. So it shows that it's not the case that we always use the most complicated program to control the task. So the algorithm is able to select a reasonable structure to control the task within reasonable number of samples. And we also try to change the max depth value to 5, 6, or 7, and it shows that we always converge to similar programs in terms of similar depths.
Thanks.
Yeah. So the other question is about how can we overcome the complexity issue of the algorithm. So I'll just quickly go over the other work that tries to solve the problem. So in this problem, it tries to do sequence classification. We want to predict a label for a sequence of input. And for this, we use a context-free DSL grammar to define a grammar over some program input over a sequence, some add function, multiplication function, some constant function, and we also have if then else, and we also have some library functions that tries to choose a subset of the features of each frame of the video and pass that into a linear function to compute a value. So for example, in this trajectory, we want to predict whether 2 mice are doing doing sniff or not doing sniff. And then we can have some library functions that extracts the position value or the distance between the two mice from a frame of the video. Okay, and then we want to use this function and also some other higher order functions to compose these structures together to get a higher order program to understand a video clip and then use the learned features as a summary of the video trajectory to predict what is the label of the video. Okay, so you see that the grammar is very complicated, and this is the program we learned to label each frame in the video trajectory regarding whether the two mice are doing sniff or not doing sniff. So because we want to predict the label of each frame, of course, we will use a map function to walk over every frame in the video clip. And then we use the position as a bias. So it turns out that if two mice are doing sniff, they are often at the bottom of the box. And we also use the distance between the two mice. If the distance of the two mice are very close, and then they are doing sniff. So we can learn such a program to do the classification. And the question is that how can we generate such a program to minimize the prediction loss between some labels and some trajectories given us as the training data? And of course, we can still build the program derivation tree. And this is not going to scale because we have a really complicated grammar. So if we continue to grow the program derivation tree, and even at depth 4, we would have many program structures. So one way to overcome the scalability issue is that we allow program structures to share node. So for example, in this grammar, with a starting symbol, we can expand the program into an add or an ITE or a map, right? We only show 3 possible architectures on each node in a program derivation tree. But because our grammar is very complicated, you can imagine there are many functions on the same node. And of course, if we do not allow node sharing, and then like this, we'll have to also we have to expand the first parameter of the add, also expand the second parameter of the add, and we also need to expand all the 3 parameters for the ITE and the parameter for the map. So this will give us a very wide tree. So in order to overcome the scalability issue, we'll just try to for all the first parameter of these partial architectures, we want them to share nodes. Okay, so we will not expand the first parameter of add, the first parameter of ITE, and the first parameter of the map separately. We will use the same node as what can be derived from the first parameter of these functions. And similarly, we also use the same node to represent what can be derived from the second parameter of add, the second parameter of ITE. And because the map function does not have a second parameter, so this is just an empty here. And we can do this. We also have a third box, which represents the third parameter of the ITE function. And the intuition of doing that is because at the end of the day, only one function from box 1 would be chosen. So it's totally fine to write the parameters of the add function, the ITE function, and the map function to share node between them. So this is the first optimization we make. So this significantly limit the width of the program derivation tree. And the second optimization we make is that we don't expand the program derivation tree at once. So we try to progressively unfold a program derivation tree. So at the beginning, we only have the starting symbol, and we just unfold the program derivation tree 2 layers. And for all the non-terminal symbols, as the second layer or the third layer, we use a neural network to represent their possible values. And then we apply the architecture synthesis and the selection algorithm to find the best structure in the 2-layer expansion. After which, we try to progressively unfold the rest of the layers. So for example, we can progressively unfold the 2 layers. And then for the rest of the non-terminals, we can still represent them using neural networks. And then we also choose the best programs on these partially expanded graphs. So this shows that we only preserve what is promising in the program derivation tree, and we filter out the unlikely program derivation search directions. And this would also significantly limit the depths we need to search at a certain point, at a specific search iteration, because we just progressively unfold the program derivation tree structure. And with these 2 optimizations, we can fit a very complicated program derivation tree into GPU, and then use data search algorithm to find the best programs structure among even very complicated program derivation tree. And that's the optimization we make in order to scale this kind of architecture search. So I hope this quickly answered your other question about the scalability of the approach. So we use these 2 strategies to limit the width and the depth of a program derivation tree to make it scalable. And it turns out, and we also compare our approach with another approach, NEAR, which is the state-of-the-art program learning method based on enumeration and heuristic search. It shows that dPads, which is R2, outperforms NEAR in terms of the F1 scores learned for trajectory classification. So I think that we have run out of time. I don't have time to talk in details about the 2 optimizations we make, but I hope those results convince you that even the grammar is very complicated, we can still think about how we can progressively doing update to the program derivation tree to make the search problem scalable.
Cool, thanks. This is amazing work. Very exciting.
Yeah, thanks.
Yeah, thanks. Thanks for the presentation.
Thank you.
All right, so bye everyone, and we'll see you next week.